Hello, it's time to place some dominoes. Let's play pips. I'm really hoping that 2 days in a row that have been absolutely embarrassing. I'm hoping I don't repeat that today. I'm sorry in advance if I do. Once again, we've got an easy puzzle by Ian Livengood and the medium and hard by Rodolfo Kirchen. We'll start with the easy. All right, let's start solving and see how this goes. All right, we need a 6 in the bottom there. Let's see, we have 2 sets of 3. So we've got 3 3s and 3 1s. Okay, so 1s and 3s. And we don't have doubles of either of them, which is good to know. How do we get this started? Let's see. This feels like it would be more difficult to achieve. Oh no, we can't do that because we need 1s and 3s. Right, sorry. So yes, of course it's not only more difficult, it's impossible to achieve. So that goes there. That's something we start with. So our less than 3 is going to be our 2 or our 0. It can't be our 0 because then our 1 would be in the wrong place. So I think what that means is this 0 goes into the void down here, and the 2 goes into the less than 3. And then we need to bridge the 1 and the 3. And finally, our 5 goes into the void, and that's the easy puzzle. It took probably a little longer than it should, but that's fine. All right, we're on to medium. Right, okay. So we need 2 of something. We've got 1s, 3s. We've got all sorts of things for that. The 10 needs to be in a single domino, which will be either this double 5 or this 6 4. We don't yet know which, I don't think. We also need a 9, which could be 6 and 3 or 5 and 4. That doesn't seem very difficult. I guess we need a greater than 4 that connects to something that could make a 9. It's not that difficult necessarily, but it might be difficult if we waste a 6 on it right off the bat, because then we'd need to connect the 3 to a 6. Then we could still make the 10 with 2 5s. I guess that's not that difficult, actually. We could even point this straight down into the 4, and we still have other 4s to make that equivalence region. Although, if we did that, actually that breaks, because then this actually doesn't work, because then we couldn't make the 6 in a single domino, which we would need to do in that situation. So, I mean, all that means is that this would have to go this way, which might still break for other reasons. I don't know. I guess we can try it and see. This would have to be double 1. Then we'd need a 2 here and a 3 here to make the 6. No, this works. This actually works. Okay, well, that wasn't a very elegant solve, but I mean, it's the medium puzzle, whatever. Got it. Let's try the hard and see how terribly I fouled this up today. Okay, so we've got an R being spelled out in the grid. Okay, we have 3 3-sized 12 regions and an 11 region, which will be 6 5, and the 6 5 has to be bridged across to the 12. It's interesting. We've got this double 6. So, I mean, this could, in theory, go here for, it's actually relatively limited where this double 6 can go, because it obviously can't. No, that's not true. I was going to say it can't go inside any of the 12 regions, but it could, because we do have 0s. It could even go here. And look, we've got all these 5s as well. Okay. We do have a 0 in the grid, but we've got 3 total 0s to play with in our dominoes. So that's not very useful. Well, let's consider, well, 0, based on the geometry of just how we're going to have to put dominoes in the grid, the 0 needs to point into that 10. Actually, okay, this is our first definite deduction. We obviously can't double the 0s in there because then the 10 is impossible. So this is where I should have started. So 0 6, done. That's correct. So now we need a 4 coming off of that 10 going into the 4 region, which obviously can't be this. So actually, this is fairly limited as well. So it could be either double 4 and we have a 0 there, or it's 4 1 and we have a 3 there. So the 0 is interesting because our only option would be to do this, in which case we would need a double 6 here. Let's see how this goes. Kind of curious to see how that plays out. Then Actually, this is interesting because our 11 now needs to be made up of 6, 5, and there's only 1 6 with which to play at this point. But it could go here or here. Well, at this point, actually, we have, at this point, this is actually a case where, you know what? This puzzle is actually a perfect candidate to do some counting. I should have seen that from the beginning because all of our regions are enumerated. And we just have these 2 void cells. So I can actually just add up the remainder of what we have. The things we have left add to 35. We've got 2 12s and 11. That adds to 35. So whatever the difference is between 35 and our current pip count is what goes in these void cells. So what is our current pip count? 10, 20, 28, 38. Right. That means we need to put only 3 pips in these 2 void cells. Yeah, this is a good way to do this. That might be impossible. No, it can't be impossible. Because we've put the correct number of pips up there. We need a 1 and a 2. I must be doing something wrong. So, sorry, let me think about this again. $38, $35. Okay, it must be that zeros need to get involved. So I think what that means is I need to rearrange these in order to allow this to work. Because what I determined was that with that arrangement of dominoes, there was no way to get a count of 3 into those void cells. I'll need to rearrange the grid in order to allow that to happen. So what that does mean is it's still true. It's still true that that count should be accurate because, even though the dominoes I put into that top region, I think were inaccurate in terms of where they were placed, they still did equal the number of pips I put up in these top regions still did actually equal the enumerations in the grid, unless I actually just made a mistake and misplaced something. But assuming I didn't do that, the overall sort of equivalence of pips and enumerations should still be accurate. So what that should mean is I'm still going to need to put a total of 3 in these 2 void cells, and that will be either 1 and 2 or 3 and 0. Now, I don't think it can be 1 and 2, which is the situation I ended up in before, which didn't work, because our only ways of making 1 and 2, because of the geometry of the grid, we need a domino that bridges this, and neither 1 nor 2 will allow us to make that 11, which means they need to be 3 and 0. Now, there are 2 ways to do 3 over here. We could do 3, 5, or we could do 0, 6. So what about, and that, similarly, pointing down to the 12, it doesn't look very difficult to achieve. We could do 3, 5, or even 00, actually. If we did 00, we'd have 2, 6 here. I mean, this would be interesting because this would be fairly constrained, because then we'd immediately need to use our other 0 pointing up into the 10. And then we'd need this 3, 5 to be over here. So I might as well try this. This is one of the possibilities. It's one of the relatively few possibilities. The 6 would need to go here. We'd then need 8 in the 12, which we could achieve with a double 4. We'd have to achieve with a double 4 in this case. Whoops. This 10 would be 6, 4. The 4 would be 1, 3. This works. Yeah, so that was a good method. I mean, I should have done that from the beginning probably, because the reason I say I should have done that from the beginning is because the grid is complete. All of the regions have explicit values in them. So I didn't need to do any hypothesizing about, well, what if this double region were 6 or 5 or 4? And we only had 2 void cells. So that makes it relatively, the possibility space there, once you figure out what the difference is, makes that relatively comprehensible, I suppose. And it was interesting that the first thing I tried, I was able to disprove using that theory. Anyway, there we have it. That was an interesting one today. I'm glad it didn't take me 20 minutes. Those were the pips. Back tomorrow. Bye for now.